You've probably seen this before, a cylinder with a cut glass-like treatment. In case you haven't, take a look at this tutorial on its design in FreeCAD. But that got me thinking, what if I want to apply that effect on a curved shape such as a sphere? It might make a nice ornament for the tree. And no, this video is not late for Christmas. It's very early for Christmas next year. Start in the part workbench creating a sphere. Make it 30 millimeters in radius. Now a sketch on the XY plane. Create an octagon on the origin as a guide sketch. Set a horizontal constraint to control the orientation. Set a radius of 30 millimeters on the construction circle. I'll add some transparency to the sphere so we can see it more clearly. Here's where we run into trouble. The next sketch above is going to be smaller than 30 millimeters. We need to know how much smaller, and I'd like FreeCAD to do the work for that. To work that out, I've created a test model. Here I've set the construction circle of the octagon sketch to be real geometry. We have a 30 millimeter radius circle to show the sphere in cross-section. We can see the edge of the octagon sketch where it intersects the sphere. This is all starting to look familiar. Flashbacks to the unit circle in high school trig, and therein lies the answer. We know the radius of the sphere, and we'll know the height of the intersecting plane. We can draw a right triangle, and that leaves the adjacent leg of the triangle along the x-axis to define the radius of the octagon. So we get the solution from our good friend and all-around cool dude, Pythagoras. So I'll select the test sketch, and in the data pane under constraints I find the radius constraint. I could have named the constraint to make it a little bit more clear, but in this case, since we only have one constraint with a numeric value, it's obviously the right one. Now apply the Pythagorean theorem. Sphere.radius squared minus placement.base.z squared. Close the parentheses and take the square root. There we have it. Change the height of the sketch, and when we recompute, the radius is set. Returning to the model, enter the formula for the sketch. Same as before, sphere.radius squared minus placement.base.z squared, and take the square root. And now we need a copy of the sketch, so use Ctrl-C to copy. Looking at the object selection, we do not need to copy the sphere. We've already got one. So uncheck the sphere and OK. Ctrl-V to paste in the copy. Select sketch 001 and in the data pane set placement.position.z to 6 millimeters. The octagon needs to be rotated so its vertices stack up along the midpoint of the sides of the first octagon. So set placement.angle to 360 divided by 16. 16 because dividing by 8 would rotate one full face, but we only want half of that. Since we have a variable radius, unlike the cylinder, we can't just make one row of cuts and then stack the result in a linear array. So there will be a lot of octagon sketches. That'll get visually confusing later. To simplify things, open the sketches and toggle all of the irrelevant sides of the octagon to construction geometry. That's going to be much easier to work with. I'll hide the sphere for now so it doesn't get in the way of selecting vertices. Just as for the cylinder, select 3 vertices forming a triangle and create a sketch on those 3 points. Bring in the 2 lines that include those 3 points as external geometry. Using the polyline tool, create the triangle on those points and close the sketch. To do the next triangle, hide that sketch to make sure the right vertices get selected. Repeat the process, forming a triangle that points the other direction. Now bring back the sketch of the first triangle. Select both of the triangle sketches and extrude to the default 10 millimeters. The exact amount of the extrusion doesn't matter, these are just cutting tools. Due to the way the sketch mapping worked out, one of the extrusions is going the wrong way. Select it and in the data pane set reverse to true. And that's the first set of cuts. It would be a gigantic pain to have to repeat that entire procedure all the way up the sphere. It might actually be doable for this small example, but it could easily get out of hand if we wanted more facets or a larger sphere. Fortunately, there's a good way to let FreeCAD do the work. Select all of that geometry except for the sphere and create a compound object out of it. Select the compound and go to Edit, Duplicate Selection. Ctrl-C and Ctrl-V will do the same thing if you prefer. In the object selection, copy everything but the sphere. The nice thing about copying it all as a compound is that we not only get copies of all of the sketches and the extrusions, but the attachments remain intact. Sketch 004 is a copy of sketch and has a placement.z of 0, and sketch 005 is a copy of sketch 001 with a z position of 6 mm. Sketches 6 and 7 are attached by 3 points to 4 and 5. Select sketch 004 and in the data pane change placement.position.z to 12 mm. We want to turn it into the upper sketch now to reverse the direction of the triangles as we work our way up the side of the sphere. As you can see, when we did that, we effectively pulled the geometry inside out so that the extrusions are now going into the sphere rather than coming out from it. That's easily fixed by selecting each of the extrusions and toggling the reversed boolean. Now they're coming out the right way. They make a bit of a mess intersecting each other, but that's really not a problem. It's just a cutting tool. Now just repeat the process, duplicating compound 001 into compound 002, once again declining to copy the sphere. Again take the sketch with the lowest z value, 6 mm, and add 12 mm, giving 18 mm to make it the upper sketch. Again reverse the direction of the extrudes. I'll fast forward a bit. And now one final time to reach the north pole of the sphere. But we need to pause for a second. The lower sketch is at 18 mm. When I add 12, it'll be at 30 mm, exactly the radius of the sphere. But at 30 mm, it's going to try to give the circle a radius of 0. The whole thing will collapse into a singularity and spit out points and lines at us as Hawking radiation. Okay, so maybe not, but the geometry engine will definitely not like it, and it's going to throw an error when it tries to divide by 0 somewhere. So cheat the numbers just a little bit and set the z value to 29.5 mm. It would probably even work at 29.995 mm, but this is just as well. I wanted to leave a little uncut space at the top. It may be a little difficult to visualize, but this is the essentials of our cutting tool to apply to the sphere. It just needs to be spread over the whole sphere. Create a polar array from the Lattice 2 workbench. As is typical, set the radius to 0. In this case, because we used an octagon, set the count to 8. Now open each of the compounds and select the extrusions and fuse. Now select the fusion, the polar array, and populate with copies. That's got the northern hemisphere covered. Now select the populated array and mirror across the XY plane. Open up the mirror, select the populated array and the mirror, and fuse. Select the sphere and the fusion and cut. Obviously this has failed. As regular viewers know, this is far from the first time this has happened, and the solution is always the same. Delete the cut, select the fusion, and connect. Effectively, this papers over any of a million tiny rounding errors that caused it to think things that should be touching were not. Now select the sphere, and the connect and cut. It's going to have to think about this a moment. Select and hide any of the extraneous extrusions, and here we have our cut crystal sphere complete with a nice star shape at the top. Thank you for watching. If you liked this video or found it useful, please like, subscribe, and share. If there's anything you'd like to see covered here, please let me know in the comments below.